Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to talk to you about another one of my articles. This one is entitled The Planet X System is Here, the Roche Limit, and Gravitation. Now, the Roche limit has been repeatedly used by debunkers and trolls to argue that it is not possible for massive objects like the ones that Scott and I have been observing near the Sun to be there. So in this article, I will be putting the Roche limit argument to rest. Using known and accepted physics research, I will also clearly show through observational evidence that the movement of stellar cores in the Sun's corona is not according to what is expected from a gravitational interaction between these objects and the Sun. Now, the Roche limit is defined as the closest distance at which an object held together only by gravity, and that's very important, held together only by gravity. This is the definition. Begins to break up due to tidal forces. So the Roche limit is the closest distance at which an object held together only by gravity begins to break up due to tidal forces. And these tidal forces can be described as different gravitational force magnitudes across a single body. And tidal forces are associated with tides on Earth, which are due to slightly different gravitational forces acting on the surface of Earth's oceans. And these are different to the gravitational force on the Earth's center of mass. And this differential is dependent on the Moon's position in relation to the Earth and the Sun. Now, as I have mentioned when I wrote an article about this, which explained what was happening with the tidal events that we have been observing recently, including the disappearance of the ocean from Brazilian shores and now from the Mississippi River. Although this is new and has happened since then, it is still the same thing. These are tidal events due to the presence of the Planet X system in the solar system. And these objects will cause the Earth to wobble, and it will lead to these strange tidal events. They are not normal. And the gravitational force is a good model and can explain it. It's not the actual force that I believe is causing it. It can all be explained in terms of the electrical and the magnetic interactions. But the gravitational force is easier to use and we can model it for a system that is in equilibrium. So I did use the gravitational force, and we can use it again to explain what is happening. It is an attractive force, and that attractive force can be due to an electrostatic interaction. The electrostatic interaction can be both attractive and repulsive, and that will become very important towards the end of this article. But for now, we can explain these tidal forces in terms of the gravitational model, and that is when the Moon and the Sun are in alignment, the attractive force on the Earth's oceans is stronger than the attractive force of both objects on the center of mass of the Earth, because the oceans are closer to the Moon. So there's an attractive force which causes the oceans to bulge out on the side of the Earth, and on this side there's an attractive force that whether the Moon is on that side or if it is on this side, then the force is less on the surface of this ocean, and that causes the attractive force between the Earth and the surface of the ocean to decrease, which leads to the ocean also bulging outwards and causing a higher high tide than normal, called the spring tide. A neap tide is caused when the Moon is at 90 degrees to the Sun's position. So these are first and third quarter Moon phases. The high tide that is produced at that time is not as high as the spring tide. Now, the stellar cores near the Sun are clearly solid, And since the density of the sun's core is believed to be 150 grams per centimeter cubed, and that is an accepted value for the density of the sun's core, and we would therefore expect stellar cores to have at least this density. And the telescopic photograph of the blue stellar core, which is shown here, and in that provides observational evidence of the fact that these objects are solid and remain solid when immersed in the sun's corona and are covered in this gaseous plasma that makes up the sun's corona. So this shows that stellar cores must be much denser than a planetary solid iron core, such as the one that our planet has, because the Earth's inner core, which has a density of 13.1 grams per centimeter cubed, that's a well-established value, would melt between 6,000 and 7,000 Kelvin. Again, this has been measured. And it is a much higher density than the density of iron at the standard temperature and pressure. The density of iron in that case is only 7.9 grams per centimeter cubed. So again, well-known value. Now, the stellar core that we see in this photograph, this was taken through a telescope. It is close to the sun. So this is the sun, this is the stellar core, it is huge. And it's solid. We can see that it's solid because it has grooves on its surface. And only a solid object can have grooves on its surface. If it was liquid, the grooves would quickly be filled in by the fluid. If it was gas, then gas expands to occupy all the space that's available, so there would be no grooves either. So the object obviously is solid, and the fact that it is in the sun's corona, you can see this is gaseous plasma coming from the stars close to the sun that have plasma around them. I don't even say anymore that this is just the sun. We do know that the sun itself was being photographed when this object was found, so we know it was very close to the sun. But the pink magenta I now associate to a rejuvenated stellar core that is always extremely close to the sun and has been observed, and well, not the whole thing has not been observed, but the color it emits, which is this magenta color, has been illuminating our atmosphere. And we do know that this stellar core is therefore very close to the sun. And it must have rejuvenated because it's emitting enough light to illuminate the Earth and cause spectacular sunsets and with the magenta color. So this object immersed in the sun's corona, which is at a temperature of millions of degrees Kelvin, does not melt. So it has to be denser than the density of the Earth's inner core. And it's therefore an extremely dense state of matter. And I have written several articles about what state I think that is, which is it's a complex plasma state. And in that state, plasma can exist in the solid phase. And it has a crystal structure. But I think the only way that this type of core can be produced is actually within a star when it is in its main sequence phase. Now, so the fact that stellar cores do not melt or vaporize in the sun's corona, where the temperature is usually between 800 Kelvin and 2 million Kelvin, means that it must be in a super dense state of matter. And this state, as I have said, is likely to be a solid phase achieved by complex plasmas in the interior of a star. And whilst it is in the main sequence state, and to I cannot go into it. I do explain how I believe that the main sequence stars age and go through different aging processes. But it is a well-known fact in astrophysics that stars, when they age, go through the red giant and the white dwarf phases. And in those phases, they lose most of the ionizing material that is part of the star in the main sequence phase. They lose their outer layers of ionizing material. Now, the temperature in the sun's corona during X-class flares actually is higher than 2 million Kelvin. It can go above 30 million Kelvin. So we are going to do a few calculations. Now, it's an accepted fact that matter in the solid phase has a higher binding energy between its constituent atoms and molecules than matter in the liquid and gaseous phase, and that this binding energy exists as a result of the electrostatic force between the constituent atoms or molecules. Now, what does that mean? That means that in the solid phase, atoms are closer to each other, and they have stronger forces between them that holds them in that position. Then you would find between atoms in the liquid and the gaseous phase. In the gaseous phase, atoms in the material are so free to move that they will expand to fill a container. Whilst in the solid phase, you see a solid will stay solid, and the layers will not even slip past each other like you would find in a liquid. So we know from that the binding forces that keeps the solid as a solid must be a lot stronger. And a lot is known about these forces, and they have been measured. And the strongest of these forces are called covalent, metallic, and ionic bonding forces. These are the strongest. We do have weaker ones called intermolecular forces, and these are called van der Waals forces. They are all electrostatic in nature, so they are produced by the electric force. Now, in a superdense state, the ionized particles in a crystal structure for solid complex plasma phase must be much closer to their near neighbors than what be expected in a normal crystal structure of, say, iron. But it is a lot easier to use iron because there are a lot of parameters that we know about that. So we're going to calculate the attractive force in the case of the gravitational interaction, and we're going to compare that with what has been measured regarding the bonding forces between these atoms in iron as well at the same density. So iron has an atomic number, which means that's the number of protons in the nucleus, of 26, and an atomic mass number of 56. The atomic mass number is the number of protons plus neutrons in the nucleus. And the nearest neighbor distance in solid iron in the BCC, or body-centered cubic crystal structure, is 2.383 angstroms. And I'm going to use R as the variable in the equation. So all of these are well-known established values. This has been measured. Then the gravitational force according to Newton's law of universal gravitation in the case of two iron atoms separated by a distance r is given by this equation, Gm mass of iron squared divided by the distance r squared. And G is the gravitational constant, Mfe is the mass of an iron atom, and r is of course the distance between neighboring atoms. So it will be given by this value. Now we can ignore the mass of electrons because it's very small compared with the mass of protons and neutrons. And because the mass of protons and neutrons are approximately the same, we're going to just use the mass of the proton in the calculation. And that is 1.67 times 10 to the minus 27 kilograms. Then the mass of iron would be the total number of protons and neutrons, which is 56, times the mass of each proton. Then the gravitational force between atoms in solid iron in a crystal structure is given by this, where G is 6.67 times 10 to the minus 11 in these units. Then 56, the atomic mass number squared times the mass of each proton squared, divided by the distance between the two. And that gives us 1.02 times 10 to the minus 41 newtons. So this is the gravitational force between two atoms in solid iron. So now let us compare that with the binding forces, which are of course electrostatic in nature, in solids with the same density. So basically, and the same crystal structure. So measurements of these binding forces ranges from 10 to the minus 7 newtons, and this is for ionic bonds, which are the strongest binding forces, to 10 to the minus 11 newtons for van der Waals forces. And these are, of course, much weaker, 4 orders of magnitude weaker. And then we have the absolute minimum forces that have been measured, and these are basically surface reconstruction forces. So the one that is important for us is actually the 2 to the minus 11, but it makes no difference because the electrostatic binding forces are at least 27 orders of magnitude stronger than the gravitational forces. So this means this is huge. This is 27 followed by 27 zeros factor difference. This is an absolute huge number. So there is a huge difference between what the gravitational force can provide as a binding force than what can be provided by electrostatic forces, and that is for the weakest ones. So if we were to work with matter in the increased density state, which stellar cores must be in, the atoms in a complex plasma crystal structure would be much closer together, and we would therefore obtain a stronger gravitational attractive force between them. But then we would also expect the electrostatic binding forces to also greatly increase in strength. And even if they do not increase in strength at the same rate, it is still impossible to make up for 27 orders of magnitude difference. Then, in addition, measurement of these binding energies at densities comparable to that believed to exist in the core of the Sun, and therefore stellar cores, shows that the binding energy increases as the density increases. So it never decreases, it never actually becomes repulsive, which would lead to the object breaking apart. It always increases. So this means that the gravitational force will not ever be able to overtake the electrostatic binding energy within a solid object. And the Roche limit is therefore a meaningless argument in this case. Now, let us look at one of the stellar cores, and this is just one of them that has been observed within CMEs. The CMEs actually highlight these objects. You can see this object is actually slightly larger than the Sun, and the size of the Sun is indicated by this white circle on the occulter. We see the object here. It's in gray because it can more clearly be seen. We can clearly see that this is a solid object with a spherical shape because we can see the circle in it on this side and on that side, indicating a solid object within the CME plasma material. So the solid spherical object made visible by this CME in figure 3, and this is from July 23rd, 2017. There was actually a huge CME at that time. And I have written before that I believe that that these objects are provoking the sun to have these huge CMEs and solar flares. So this object is obviously in the sun's corona. It is within the CME plasma, and this object remains as a large solid body in the extreme environment of the corona, as seen here, which establishes it as a stellar core, a star that has aged and its core has been exposed through that aging process, and it has come to the sun because it is attracted to the sun. And this is why it is so close to it. But we're going to see that there's something that shows that the fact that this object is here it means actually that it's not attracted gravitationally to the sun. The gravitation does not seem to play a part at all in the interaction between the sun and this body. So the object is obviously larger than the sun, yet it is seen moving away with the sun at about the same rate as the CME material. And you can see it in both these images, also LASCO C2 images. This image is from 6 UTC. This one is from 5:48, 12 minutes before that, and this one is from 6:12. So there's a difference of 24 minutes between these images, and in that time the object moves from here to there. You can clearly see this is the distance between the edge of the occulter to the edge of the object here, and this is the distance from the edge of the occulter to where the edge of the object is over there. So the object is obviously moving away from the sun as the CME moves away from the sun as well. So that would mean that the object would have to have the same acceleration as the CME material. Now, in order for both the CME and the CME plasma and the stellar core to have the same acceleration away from the sun, they have to be experiencing a repulsive force, which is able to overcome any possible gravitational attraction. The gravitational force is, of course, proportional to mass, and it should be obvious that the stellar core is much more massive than the gaseous plasma in the CME material. So the gravitational force to be overcome by the explosive force, because this is usually explained in terms of an explosive force, an explosion happens on the body, and this explosive force would have to be different for both objects, that is the plasma material and the stellar core. The stellar core is the size larger than the sun. So in terms of the gravitational force, and it's the core, extremely dense, it would be a lot more massive than the sun itself. And yet an explosion leads to it having the same acceleration as CME material. Is that possible? No, it's not possible. The only type of force that could lead both plasma and stellar core to move away from the sun with the same acceleration has to be independent of mass. If it is dependent on the mass, it is impossible for the objects to have the same acceleration. The electric force is the only known force to be able to do what we observe and to cause both plasma and stellar core to move away from the sun with the same acceleration as a result of electrostatic repulsion. The electric force is, of course, independent of mass. It depends on charge, and it is possible through a process of polarization or whatever else, just that the two objects, the plasma and the stellar core, achieve the same degree of polarization and therefore experience the same repulsive force. So the fact that gravity, if it was acting at all, is not able to keep such a large solid object attached to the sun, and because it's so large and so dense, it would have to be more massive than the sun itself, shows that gravity cannot be exerting any influence at all, and is not the primary force that it has been believed to be up to now. My argument has always been that observation should speak for itself, and that if there is any theory that does not agree with the observation, it is falsified and needs to be reworked. Now, observation clearly indicates that stellar cores are extremely close to the sun and are often observed in the sun's corona and moving through it. If the current established theory cannot agree with it, then the theory needs to change. However, there is no doubt that even though the gravitational theory cannot explain the interaction between stellar cores, as these are both attracted and repulsed by the sun, and the gravitational force is an attractive force only, it is still a useful model for calculating orbits because it is so easy to use in comparison with the electrical and magnetic forces which give rise to its effect, but are much more complex and therefore more difficult to make calculations with. Nevertheless, the gravitational interaction, although a good model for solar system objects, in other words, in the case of one star and planets in an equilibrium state, it clearly cannot be applied to what we have happening in our solar system, which is the merging of star systems that must of necessity not be in equilibrium. An equilibrium state is a state in which all objects in the system are in stable orbits. This is what I mean by an equilibrium state. When star systems merge, there is a dynamic change going on in the nucleus of the new system. Orbits are changing and objects may spiral inwards or outwards towards a center point that is constantly changing positions. So in conclusion, the Roche limit argument used by debunkers and trolls is a meaningless argument as a result of its own definition. It is an ignorant argument used by those who would cover up the truth. The motion of stellar cores in the sun's corona, with their presence being highlighted by CMEs, clearly indicate that gravity is not a real primary force. Gravity can only be used as a model in special equilibrium conditions, such as in the solar system when it is in equilibrium. The solar system is no longer in equilibrium because of the additional planet X system which is merging with it. And in addition, I would like to give you an opportunity to look at my references. And here we have temperatures in the Earth's core based on melting and phase transformation experiments on iron, density and composition of the mantle core. These give us certain of the measured values regarding the density of the Earth and the density of iron. And complex plasma is a model for the quark-gluon plasma liquid. This is a very good article on complex plasmas and statistical properties of superhot solar flares. And this talks about how hot the corona is. Then we have, I actually forget what this one was about, but some more values that I needed. And then the structural properties of iron crystals, atomic force microscope, which had the value for the nearest neighbor distance between ion atoms in an ion crystal structure. And then finally, achieving high density states through shock wave loading of precompressed samples, which contains the measurement of the binding energy of densities up to what we'd expect to have in the sun's core. So this is Dr. Claudia Albers, Planet X physicist. Thank you for watching.